Today we are going to talk about uncertainty principle and its application in the quantum physics world. In quantum physics, the uncertainty principle or Heisenberg's principle is one of the many mathematical inequalities which asserts a fundamental limit, the precision with which the position and momentum of a certain particle can be determined simultaneously. The wave group shown here clearly explains what is involved. The particle related to this wave group may be located anywhere within the group in given time. Probability density chi square is obviously maximum in the middle of the group, but then the particle may be present anywhere where the probability density is more than 0. In the narrower wave group, the position of the particle is more precisely determined, but due to insufficient waves lambda cannot be measured accurately, and hence by de Broglie's equation, equal momentum cannot be measured properly. In the wider wave group, there is clearly defined wavelength, hence we get momentum as the more precise quantity. However, the wave group is far too wide for us to actually determine the position of the particle. The theory was first proposed in 1927 by the German physicist Werner Heisenberg. He stated that the more precisely the position of some particles is determined, the less precisely its momentum is known, and vice versa. The formal inequality relates the change in position of the particle and the momentum with Planck's constant. This theory arose because basically matter can behave both like waves and particles. Mathematically, the equation ID is represented as del x into del p is more than equals to h cross by 2, where h cross is equal to h by 2 pi, where h is Planck's constant. Historically, the uncertainty principle has been confused with a somewhat similar effect in physics called the observer effect, which notes that measurements of certain systems cannot be made without affecting the systems. Heisenberg offered such an observer effect at the quantum level as a physical explanation of quantum uncertainty. Here, a simple example of formation of wave groups is shown. Two wave trains slightly different in angular frequency omega and wave number k are supposed to yield the series of groups as shown. A moving body, however, corresponds to a single wave group, not a series, but a single wave group can also be formed by superimposing a train of harmonic waves. But an infinite number of wave trains with different aspects is required for an isolated arbitrary shape. Here I will be showing the derivation of Heisenberg's uncertainty principle. We know de Broglie wavelength of a particle of momentum p is lambda equals to h by p, and the corresponding wave number is k equals to 2 pi by lambda equals to 2 pi p by h. Particle's momentum is hence p equals to hk by 2 pi. Hence, uncertainty del k in the wave number of the de Broglie waves associated with the particle results in an uncertainty del p in the particle's momentum according to the formula del p equals to h del k by 2 pi. That is, since del x into del k is more than equal to half, del k more than equals to 1 by 2 del x, uncertainty principle, del x into del p is more than equals to h by 4 pi. Application of the uncertainty principle. The limitations imposed by the uncertainty principle makes it significant only in the aspect of atoms. This is due to the small value of Planck's constant. The application of uncertainty principle, the limitations imposed by the uncertainty principle makes it significant only in aspect of atoms. This is due to the very small value of Planck's constant. The application of uncertainty principle is large on atomic scale and helps a great deal in understanding many phenomena. The lower limit of h cross by 2 for del x into del p is rarely attained. Another application of uncertainty principle is explaining the non-existence of electrons inside a nucleus. The radii of a typical nucleus is about 10 to the power minus 14 meter. For an electron to be confined within a nucleus, the uncertainty in its position should be nearly equal to 10 to the power minus 14. The corresponding uncertainty in the momentum is del p almost equal to h by del x almost equal to 6.6 into 10 to the power minus 34 by 10 to the power minus 14 almost equal to 6.6 into 10 to the power minus 20 kg meter per second. Therefore, the momentum of the electron must be at least comparable in magnitude with an electron whose momentum is 6.6 into 10 to the power minus 20 kg meter per second has a kinetic energy almost equal to 10 to the power minus 9 joule, many times greater than its rest energy m naught c square, which is almost equal to 10 to the power minus 13 joule, and we may accordingly use E square equals to c square into p square plus m naught square into c to the power 4. Neglecting m naught square into c to the power 4 because mass of electron is very less, E square is almost equal to c square into p square, or E is almost equal to c into p. E is almost equal to c into p, which means 6 into 6 into 10 to the power minus 20 into 3 into 10 to the power 8. E is almost equal to 2 into 10 to the power minus 11 joule, which is almost equal to 2 into 10 to the power 11 by 1.6 into 10 to the power minus 9 electron volt equal to 125 milli electron volt, almost equal to 125 mega electron volt. Thus, the kinetic energy of an electron must be of the order of 125 mega electron volt if it has to stay inside the nucleus. The experiments indicate that the electrons associated with unstable atoms never have more than a fraction of this energy. Therefore, we conclude that electrons cannot exist within the nuclei.
Go.
Another aspect of uncertainty is applied in energy and time. The limited time in an atomic process limits the accuracy with which one can determine the frequency of the waves. To measure energy E emitted in the time interval t, where energy is in form of electromagnetic wave, we will make an assumption that the minimum uncertainty in the number of waves we count in a wave group is one wave. Since the frequency of the waves under study is equal to the number of them we count divided by the time interval, the uncertainty del nu in our frequency measurement is del E is equals to h del nu. So, del E is more than equal to h by del t, or del E into del t is more than equal to h. Therefore, del E into del t is more than equals to h cross by 2.
Go.
Thank you. That is all.